Ready? Sweet. Awesome. Hi, everybody. I am going to tell you a little bit about linear models for astronomers. I've gone back and forth about what to call this. Just a really quick about me to get started. So my name is Christina Hedges. I'm a British astronomer. I previously worked for the Kepler K2 mission as a support scientist at NASA Ames, where I did a lot of software development, modeling, working with the community, and research on exoplanet discovery and transits. Now I work for the Test Science Support Center at NASA Goddard, where we do a lot of support for the community that looks like building different tools, making different products. We go to a lot of different events and we run the general investigation pool. If anybody is interested in knowing more about what it's like to work in missions at NASA with mission data, anything like this, please let me know. We're going for lunch today. I'm here tomorrow and I'm leaving mid-afternoon. So if anybody wants to grab me then, here, come say hi. I really like linear models. That's a weird thing to really like, but it's sort of become the way that I tend to do my data analysis on Kepler and K2 data. I know that it originally said Gaussian processes in the GitHub, and so I made this meme. It says, "Mom, can we have Gaussian processes?" No, there's Gaussian processes at home, and the Gaussian processes we have at home are that equation. I don't know how funny this is. Have people seen this equation? It's like, no, I've never seen it in my life. You may not have seen it in this format. By the end of all of my time up here yelling at you about linear algebra, you're hopefully going to recognize that equation and think that this is a really funny name. Okay, so what are we going to do? So linear models are a really powerful way to model all sorts of things, but time series especially. We're going to break it down, talk about what it is, understand why it works so well, figure out how we can fit them, and look at what it might enable us to do. After I finish yelling at you about them, we're going to do some work on real data, real Kepler data, real test data, and we're going to do some of that together and some of that just you guys, and I'll walk around and help you. Okay, so to like cue this up, in astronomy, we often have lots of different signals inside of our data. Here, you're probably going to be concerned with 1D time series, but there's also imaging data that you're going to be concerned with that. Images over time, this concept of 3D data, and then maybe higher dimensional data from catalogs. Inside your data, you're frequently going to have something that we call systematics, this kind of catch-all phrase that holds inside it, oh, it's just stuff that I don't want. Systematics might be, oh, there's an offset in my image that I don't want. It might be that there is some predictable signal in my data because my spacecraft temperature keeps changing. It might be that there is a significant increase in my spectrum at one side of the detector. There's just this systematic increase. There's all sorts of systematics like this, and it really is a catch-all for thing that is not astrophysics that I don't want. How do we get down to the true flux of the star, or what the true image should look like in the presence of this systematic? And crucially, how do we do it fast? We're going to have to come up with a model for our data. And one of the things that we might want is that our model is pretty interpretable. We can have a model for systematics that is just hand-wavy, that is like, oh, I don't know, some function, some Gaussian process, something that I don't understand. Or we can have a slightly more interpretable model, which might say things like, I understand the temperature of my detector. I understand that it changes. Is my systematic correlated with that? So we're going to do this modeling with linear models. There might be a lot for us to cover, and we're going to go forward, and then when we take a break, we'll do some of the workbook material. I'm going to try not to go too fast. Just hands up, wave at me, whoa, whoa, go back, start again. Okay, in this, I'm going to use a few conventions, which I think are pretty common. We're going to say that lowercase, normal math letters, LaTeX letters, normal italic letters, that's a single numeric value. If I'm using a bold lowercase letter, that's a vector. If I'm using a bold uppercase letter, that's a matrix. This is a fairly common convention, I think. But when we're looking at any of the equations in these slides, That's what I'm usually meaning. It's harder to do that in Python. I think most people here are comfortable with coding in Python most likely. If you're more comfortable coding in R, C, and you're not following this too quickly, wave and ask me to qualitatively describe what's going on. I'm going to be working in Python with this notebook. I'm trying to follow the convention, which is like, okay, a single number is now going to be A0, A1, that's a single number. Lowercase letter is a vector, uppercase letter is a matrix. Okay, let's go through writing down sets of linear equations. What is a linear model? Okay, linear model, I know that you guys potentially have lots of experience doing this. I'm going to go over it, and I'm not going to go too fast because we've also heard a lot about Fourier transforms, and we're all like queued up thinking about things in Fourier space. So just to recap, linear models. Here I have a linear model of y. It's linearly related to x. I can take x, multiply it by some coefficients, add in some coefficients, and then get y. There is not a linear relationship between x and y in the second equation down. There is not a simple coefficient that I can multiply that part of the equation by to get, multiply x by to get y. The equation at the bottom, the relationship between z is nonlinear, but x is linear. Don't dilly-dally too much on this. Keep going. Wave at me. Before, no, it isn't. Christina, stop. Okay, matrix notation. We're gonna try and do matrix notation. I just want to say, if your understanding of matrices is like vibes, that's my understanding of matrices. Like, oh yeah, we just take the dot product. I'm like, yeah, which one is that again? It's okay. The squares, the shapes, the vectors, it's truly okay if your understanding is also just vibes. We'll move on and get some data in it. In general, though, I'm going to try and say we've got this vector y. I'm going to take this matrix and I'm going to dot it with a different vector w. My matrix is a function of x, and then I have these ones, and then w, I have just the two coefficients that I'm going to multiply by each of those elements in the matrix. You can see that this is equivalent to this in matrix notation. Sweet. Any thoughts before I keep moving on? Okay, we can write our equation y 2x plus 3. I can rewrite it here. Our coefficients then are 2 and 3, and I'm going to multiply them by first our x, and then you can see here. Oh, thank you very much. Here, this is x to the 0. We're going to be coming back to this term in our matrix, which is the column of ones, and you'll see that it becomes important. In fact, Ryan's actually implicitly talked about this column of ones when he was talking about Fourier series. We will come back to this. Okay, so that was a little small in terms of our linear model. So we're going to look at how we might build slightly bigger ones. This is the same thing here. We have this y vector is our A matrix, starting with our W vector. Now though, my A matrix is just a bit bigger and I have lots more weights. In this case, I have all of these different vectors, which are functions of x. And then I have these weights that I'm going to dot with them in order to make y. This is the way that we would write that if we were writing it now. We can make polynomials, which are really handy when we are fitting lots of different things, but especially some small parts of time. We can use polynomials, and you can see here my matrix is now, I've said time is the vector, some time t. I can take time to arbitrary powers, dot them with that number of weights, and then I'll have a polynomial in time. And that's how I'm going to write it. Cool. Let's fit some models. So let's say I have this system of linear equations, which is literally cribbed from the Wikipedia page. They're exact equations. Go there if you want this in more detail. Let's write this out in Python though. I have my y, which is a vector, so mentioned this is lowercase y, here's my vector, and then I have my uppercase A matrix. And this is just me rewriting the parts of this equation out. I'm going to try and solve this equation. There's lots of different ways that you can solve sets of linear equations. I did leave some guidelines to talk about literally in the hardware. literally mathematically. How are you going to solve it? Luckily for us, NumPy rolls that up and says, here is a way to solve it, and actually uses LU decomposition. Very welcome to dig into the mathematical and computational reasons that this can be solved. But for now, let's use that solve function. We're going to find W given our A and Y. Literally do. Sweet, gave us the answer. Them's the answers, that's the W. We can put these back in and show that we do indeed get those values. I guess I didn't do that in these slides. If you take these values and you pop them in here as X, Y, and Z, you'll find that that is the solution to the equation. Okay, we very rarely have data that looks like this in astronomy, so let's try and apply it to something that's maybe a little bit similar.
That's good.
Yes, yes, yes.
So the system of equations you showed. So here A is the coefficients of the X, Y, Z, right?
Yes.
And W is the 1 minus 2, 0.
Say it one more time.
What is W here?
Oh, it's X, Y, and Z.
Oh, that's a variable. Okay.
Yes.
Oh.
Okay. I think this will become clearer when I try to do this in sort of slightly more astronomy way. I'm just going to make up some astronomy data. I'm going to say that I've taken some observations. I'm going to say I've taken 200 observations. And in this weird case, I know the process that makes it. It's polynomial and it's fourth order. I'm using Python. I'm going to make that big data. I am creating down here the true weights. And I have set it up purposefully to be a random normal so that I don't know what they are. I've made this design matrix by saying, okay, I have this vector, which I know is a polynomial, and this here, which, oh, I can highlight this part here, in Python is saying, take the vector x to the power of some index where the index ranges between 0 and 3. And then I've stacked them together so that I'm making that matrix. It's tall, it's 200 tall, it's skinny, it's got 4 vectors in it. I'm going to be doing that in Python a lot in these slides. Wave at me, it's like, wait, tell us one more time, what is this thing doing? Then all I've done is I've made some data. I've taken that matrix and I've dotted it with the true weights. This is my truth, my astrophysical truth, and then I've added some random ones. Right, there it is. That could be something, who knows? Let's try fitting it. Okay, so we're going to do the same thing. We've got A, we're going to try and find W. Let's use NumPy solve. Okay, this will not work. This will not work because you have to have the same number of variables that you're looking for as equations. This has to be square. A here is not square. As we talked about, it's 200 tall and it's 4 across. There's no way that we can just put this into NumPy solve and get the answer out. We're going to have to do something else. Okay, so we're going to build the normal equation. You guys have potentially used, heard of, worked through the normal equation, but once you understand why it's working, I find it very satisfying. So we're going to go through that. Let's try to unpack what it is that we're doing when we're trying to fit this model to the data. We have a hypothesis where we have a set of weights that when dotted with this matrix will give us a good fit to the data. We're going to have this input or this matrix, which I've now renamed X. We're going to have this matrix, which is a stack of many vectors, which are themselves written out like this in individual statements. We can write out our hypothesis function that we think that some W dotted with each part of this vector, that's what we think the model looks like. We then want to try and figure out, okay, where does it fit really good? And we're going to try and minimize the residuals. It makes a ton of sense. We do that all the time. We usually just want to fit a model to data. So to find the best fitting model, we're going to have to minimize the residuals in this model fit. To do that, we're going to write down some sort of cost function. Not a cost we write down. Not going to write, read or write that with this. Here is our cost function. This function tells us in a single numeric value, how well does this fit? You can see it's literally effectively chi-squared. You just want to find, okay, what is the number, the single number that tells me, is it a good fit or not? If J is really, really small, it's a very good fit. We can rewrite this in matrix notation, which we will come back to, and this will become really handy. You can see that my model is x.w, my residuals are x.w minus y, and this is the way that we would rewrite that square part. Here's our data back again. Remember, we have 200 elements in it. We have 4 vectors. This is the first part of our matrix. You can see in the first column, we have this column of 1, which is x to the 0, and then it's x to the 1, x to the 2, x to the 3. Okay, let's try some stuff. Let's guess some weights. Let's see what happens if we guess some weights. So I'm going to guess some random normally drawn weights. I'm going to put them into my cost function, and then I'm going to look at the results of the cost. You can see here I put in these random weights, and I get a single function, a single number out. The number is 300. It's 300 cost. Don't really know what that means, but we can take a couple of different draws and then plot them. Okay, on the screen now, I have our original data in black. You can see it has a little bit of noise, it has that curve. And then I have lots and lots of draws of random weights that I've dotted with my matrix and I've put them on the screen. Anywhere that's blue is a pretty good fit. Anywhere that's red is a worse fit. You can see that things get more blue the closer things are to the data. Right. If we guess really close, then it's going to be close to 0. But this is crap. I really don't want this. We don't want to know how good are we at guessing. We want to know what is the answer. What are the best fitting weights? And to do that, we have to know, where does this cost function turn over? Where's the minimum of this cost function? We want to know, where's the gradient of that cost function with respect to the weights with 0. We want to take the partial derivative of this function with respect to our weights. Okay, this is it. We're not going to go over it. We don't have time. I don't want to do it. You don't want me to do it. You can see at the very top, that's the residual squared that we had before. And you are very welcome in the hard-working part to go through this and rederive it if you would like. Once you go through this derivation, you'll get to the bottom and you'll find this. The weights are the design matrix transposed and dotted with itself, inverted, dotted with the design matrix transposed, dotted with the data. That doesn't feel intuitive. That doesn't sound like something that I can qualitatively say is nice. But when you take the cost function, you take the derivative with respect to the weights, that's where it's minimized. That's where our best fit is. Right. Well, we've derived it. Let's go and use it. This is the normal equation. This tells us where the best fitting weights are. We're going to have to find our weights. If you look at this equation, you can see that AT.A is square. We can now use our numpy solve again, because we have this matrix that we need to use to solve. We can, and if it is square, we can put it in numpy solve. We can use LU decomposition again. Fantastic. This is me doing that. So remember before, I had matrix in here, and then I had vector. Now I'm doing numpy, then solve, that great LU decomposition equation. I'm putting in my square design matrix transpose dotted with itself. I'm putting in my design matrix dotted with my data. And when I solve that, I get the best fitting weights out. Remember that this is 200 tall by 4 across, so I get 4 weights out. Sweet, let's put it in. Now it's the same plot on the screen as before, but this time I've also added a green line, which is what happens when I get those numbers. Give me one sec. And you can see that the green line now goes through the data really nicely. And if we print the cost function, you can see that it's very small, much less than 300. All this to say, using this equation is functionally equivalent to saying what is the best fitting weights, where does this function turn over? What's the lowest part of the cost function? That's a question.
Yeah, I just want to how we can share that
How are you ensuring that you are not getting a local minimum? The answer to this question is sort of coming up soon. Can I get you to re-ask this in the next few sections? Because this is a good question. Okay, yes.
Could you explain again why we were able to make the matrix square?
Yes. When we take the transpose and we dot it with itself, we're doing that operation where we take a tall, narrow thing, transpose it, and now we get a squat, long thing, and then we take the product of them, and then we get a small square thing.
Yeah.
Does that make sense? And so now this is square. I honestly find this, I know this is really, maybe not something to brag about, but I find this so satisfying. It's I've often used the normal equation inside of my work without realizing what is it fundamentally doing. And the fact that it is just finding that minimum of this cost function, I find it very satisfying. Okay, we're fitting models to data. Some of the niceties about doing this is if you have now found the best fitting weights using your data, it's very easy to then take those weights and figure out what is my model outside of that data. Let's take a look at our data again. Here's our best fitting model. I've built this design matrix A, and it's just a function of time. It's polynomial of time. That means that if I know time outside of this range, I can just create a new design matrix and put the weights in. So here, instead of it being between -1 and 1, -1 and -1, I've created a new design matrix between -1.2 and -1. I've made that into a matrix, and then I've dotted it with my best fitting weights. Now I can add this little piece of my model, which extends it out beyond the range of the original fit. We're going to come back to this model. So, because we have a model that's very interpretable, it is literally a polynomial of time, we can now predict that model at any location, given the weights that we fit. I am going to I don't want to mess with the time, Brian. This would be a really good time for us to stop and go through 2 of the workbooks, which kind of just give the basics of this like matrix manipulation. So it'd be a really good time to go through them. It's 11:30 and we're breaking in 30 minutes. Is that in 30 minutes? Is that right?
Yeah.
So either we can skip over basics till after lunch, which is also a really valid thing. Or we could do 30 minutes of basics workbook now. If we skip over this and come back to this after lunch.
Yeah, I think that's
Skip over this and come back to this after lunch. Okay, great. After lunch, we're going to go through just 2 pretty simple workbooks. The first of which will just step you through the basics of using that equation in that polynomial case. And then it's going to go through a realistic example, this time with Kepler data. Once we've gone through that workbook, I'm going to bring it up on screen, the one with Kepler, so that we can talk it through again.
sorry. This is sort of relative for that, but I'm a little bit confused how you go from the initial matrix and initial functions to generate the data. Like, how did the A matrix that generate the plot of the data?
In fact, actually, that's a great question. How are you generating this data? Let me. I'm going to generate some more data, so I will hover on exactly that point. Okay, we're going to go back to basics after lunch, but for now, let's talk about improving this model. We want to build a better model in astrophysics. We so rarely are actually going to fit something that's just a polynomial. Maybe we want to fit things that are exoplanet transits. Maybe we want to fit underlying stellar variability. This is also something that you're going to be working on after lunch. So it's okay if we like hover on this, but you will be working on similar notebook after lunch. Is everybody comfortable with exoplanets as a concept? Right. Just this periodic little rocks, they come back, they block a little bit of starlight, and then they go away again. I'm going to bring up an exoplanet system from Kepler, it's Kepler 10. I have written down the period, the T0, and the duration of these transits. That is, how often is it going to come back? When is phase 0? And how long will it be blocking the star for? Right. We can make lots of complicated models for transits, but right now, I'm going to just use a simple box. The reason I want to do this is a fairly good approximation, certainly better than nothing, and it's going to help me fit other parts of the model. Let's calculate that box. Okay. This is where we're going to make some big data. What I've done here is I have created a design matrix, which is that what I'm calling that X with that A, that matrix that we're going to dot with some weights. I've done it in Python. If you're like not super comfortable in Python, this part may need some explaining. I've taken some X, which is my time. I've taken away that T0. I've then taken the modulus of that with the period, and then I've asked where is this less than the duration. All this does is create a box. The box is 1 during transit and 0 outside. And I've actually taken the negative of it, and you'll see why in a minute. I've done this, oh, that's really frustrating. Cut off entirely, if you were to extend the screen out this way, this is a function, this is a list comprehension and it steps through the 2 planets. This design matrix now is as many times as we have by 2. Here, I'm plotting the design matrix. Blue is the first vector and orange is the second vector. This is one of the planets, and then the orange one is the longer period planet. Simple box, that's all we've done. Now we can try weights in there and see what that does. I've taken that matrix and I've dotted it with 2, not entirely random, but semi-random weights. This is how I'm making that fake data. I take that matrix and I dot it with weights, where weights might be a random draw, it might be the best fitting weights, it might be some prior information that I already have. When I take my 2 vectors and I dot it with these 2 weights, I'm then getting back a vector which is a function of time and has as many elements as I have times. So I've taken something that was time by n, dotted it with n weights, and I've gotten back something which is a vector with n times an element. Okay, I've got this linear model for my exoplanet transits. It's going to allow me to fit their depths. I think because I skipped over this makes less sense. Okay, here is the data for Kepler 10. Kepler 10, exoplanet transit, target, it's from Kepler, beautiful, exquisite data from pre-test time. The data is in black, the model that we made is in red, and here I have fit the best fitting weights. Well, this really does make less sense if I skip over the previous section. I'm sorry, Brian, now I've messed up my order entirely. It makes way less sense now. Says me right. All right, we'll go back slightly because the data that I was just showing you, that there's no model in it now. You can see now very clearly, because I've taken this detour to talk to you about planets and transit, that there's a planet transiting in this data. You can see that there's a big transit right here, and there's lots of little transits that are passing through here. If we want to build a model of this data, we don't account for any of the planets, we could try our silly polynomial again. This is the design matrix for that silly polynomial again. Before I move on, remember that I had before, I had my time, and then it's to the power of some number, where number is the range between 0 and 2 this time, inclusive. That's my A, so it's going to be as many times as I have by 3, 0, 1, 2. I did something different here. I don't want to like call on people. Is it really super obvious, the thing that I did slightly differently? And I can say it's this. Does anyone want to comment on that? You don't have to. Did somebody say normalizing? Normalizing. It's not quite normalizing, but that's exactly the point. It's whitening, say. This is where we take our data, which had a mean here of 140. If I have 140 squared, cubed, power 4, power 5, it becomes a very big number very, very quickly. We don't want to set up a situation just in terms of computing where we're trying to fit an insanely small number and an insanely large number at the same time. So if I take away this mean, then I'm going to get numbers that are close to 0 to the power of 1, 2, 3, 4. Sweet. There's my design matrix. Three vectors as many times as I have. There's that thing. Cool. Here we go. Normal equation. Love it. Best fitting weights. Literally mathematically the turning point of this equation. Those are they. If we plot this, this looks like a line that goes through data. If I gave you this model and I was like, I fit it, I did it, I did the science, you'd be like, yeah, you did. Good job, buddy. Probably not. Does anyone want to lambast me for things that I've done, like obviously not great?
Where are the transits?
Where are the transits? Where are the transits? There are cases where I maybe don't know about the transits. For example, if I'm looking for exoplanet transits, I don't know that they're there. I might want to do something that's like, okay, this is a guess initially, and then refine it, do some sort of Foxley squared, do something like that. But I told you there are transits, I didn't include them. if I wanted to fit the planets, I need to take into account what is the star doing. If I want to fit the star, I need to take into account what is the planet doing. Also, the polynomial is not a good model. All right, we can improve this. First off, I didn't take into account any of the planets. Let's say that I didn't give you the period of T0. What could I do? The first thing that you could do to try to improve this fit is masking. If you didn't know that that was an exoplanet transit, you might say, oh, they're these weird outliers that I don't want to constrain my fit. I know those don't come from the process that I'm trying to model, so maybe I'm going to mask them out. There are other things that you might want to mask out. For example, cosmic rays might be something that you want to mask out in your data. Flares might be something that you want to mask out if you're trying to fit stars. So this is a handy tool that you might want to use. How's that going to work? Let's try some sigma clipping. Okay, I have used probably AstroPi's sigma clipping in order to just identify which of these points are 3 sigma away, 4 sigma away, 5 sigma away. And it's highlighting all of these red points down at the bottom. Okay, I know which points that I want to treat as outliers. It's a whole other question, like, okay, how are you going to figure out which ones are outliers? I'm not going to answer this right now. Here are some red points I don't want to include in my fit. The nice thing about doing this is that if I have this design matrix and I want to fit to find the best fitting weights, I can just ask the question, what are the best fitting weights if you don't include those points? What are the best fitting weights if I say fit everything that isn't an outlier? And I will still get W back, and then I can dot it back into my full matrix. It's really handy. Yeah.
Yeah, I'm curious if like putting out some like bad data is a common way to deal with that, because from like statistical point of view, it is like it will increase your uncertainty.
That's correct.
You removing the data.
Yep.
And it's also if you have like really sensitive fitting model, like Gaussian processes or like polynomials, like then you don't really know how to put them out. So
Yeah.
I'm curious in our science cases how common and like I guess okay it is to click out some data that you don't want.
So, okay, the question I believe is, should we be clipping these outliers? Like, is this a useful tool for us to be using in astronomy? What are the implications of this? And I will say, I'm giving you this first, and we're obviously going to model the transits later. It is implicit in this question is, how am I going to know, given this data, which pieces of it are not from the distribution that I'm trying to fit? And that is information you just are not going to have most of the time. You are able to do things like, oh, this is a N sigma outlier. I don't want to treat that as part of my model. You can do things like jackknifing to see if that's something that's true. You could create a model that includes those outliers. There are, in astronomy, because we're taking physical data, sometimes somebody hits the telescope, and then we know to get rid of that point. We're going to come back to this when we look at some K2 data. Masking is useful, but it's not as good as modeling it out if you can. And we'll see that in a sec. Cool, here's our fit. It looks basically the same. That's because my polynomial model is really bad. We shouldn't be fitting with a polynomial. We have to be careful.
Is it that a polynomial model is bad, or is that the degree polynomial is bad?
See now, the question was, is it a bad model, or is it that degree 3 is a bad model? It is a bad model in the sense that you are all comfortable with the fact that this star is not modeled by a polynomial. You know full well that I can't predict what this star will do 10 years in the future, just given time and some order of polynomial. You also know that if you were to use a 10th, 20th order polynomial, maybe you could capture this information. Maybe you could capture this kind of trend here. But then as soon as you went outside of this range, that function is going to blow up in a way that you know is completely unpredictable. So I would say this is a bad model because it does not contain within it the information that I know, my prior knowledge of what the underlying process might look like. That being said, polynomials are really handy to fit other things. Let's say that I wanted to fit the planets instead of the star. It's really handy to just have some sort of nuisance that I can easily make in order to fit around it. Have to be really careful not to mask out too many points. we're implicitly weighting certain points when we do this. We're going to come back to how can we do it more correctly? How can we weight these more correctly? Cool, we're back. Here's our design matrix again that we're going to use to fit the planets. Remember, this is as many times as we have by 2, we have 2 different planets. I'm just dotting them with some random weights to show I will get some vector. This is the polynomial that we had, which is as many times as we have time, and then times the 0, times the 1, times the 2. And then this is the planets. We have planet A and planet B and planet C. Now what I can do is I can smush them together. I can literally just take those 2 matrices and stack them like this in order to get something which has as many entries as there are times, and now 5 vectors. And all I'm saying is that my model is just some polynomial plus my transit model. Let's fit that simultaneously now. So now, instead of fitting just A or just planets, I'm fitting A and planet, the star and the planets in the same matrix, and I'm finding the best fitting weights. What I've done here is ask the question, what is the best fitting weight for the planets, given that there is some function of the star? So still not a good model. What we're able to do here is fit the stellar variability accounting for the planets, or fit to find the transit depths accounting for the fact that the star is changing.
Just for clarity, your transit model is, I think you were talking about previously, so it's like the boxes of like 0s and 1s.
Yes, in fact, we can just come back up here and just look at that one more time. It is just a box. It's actually -1 during transit, and it's 0 everywhere else. I can just tell you why I've done this. If anybody has any, like, no, I get it. I know why you made this -1 instead of 1. Who knows?
But it's decreasing.
It's decreasing. It's decreasing. That's always going to decrease. And I want something out in these weights. The nice thing about a model like this is the weights are actually very interpretable. The weight that I get when I fit this is the transit depth. It's a physical quantity. It is the best fitting transit depth given the other model that I've made, allowing for the fact that my model of my transit is a silly box. So when I get these best fitting weights out, the weights that I needed to fit this, it's the best fitting weights, that's the transit depth. By making the design matrix go between 0 and -1, the weights I get out are positive. And it's the transit depth, which we would report as a positive number. We wouldn't say that I had -1% transit depth, we would say I had a 1% transit depth.
Prior, you were fitting the stars, right? We would fit that with the higher order polynomial, something more complicated than that. Fit what looks to me something like a continuum. Is that not another way? Or just subtract that off and explain it behavior independently?
You're just like teeing me up.
Oh, sorry.
No, this is great. That you're just like, yeah, what if we do it this way? Okay, so I think the question is that, Christina, you just fit the stellar variability. Why didn't you fit the stellar variability, subtract it out, and then fit the transit depth? Yes, such a great question. If we do this, you are not asking the question, what is the transit depth given any stellar variability that fits? You're asking the question, what is the transit depth if I take the maximum likelihood stellar variability, given that I didn't mask out the transits? And so if you do this simultaneously, the thing that you're able to do is calculate the transit depth in this instance, and fold in your uncertainties that come about from the fact that you actually don't know the model for the stellar variability. Does that come across clearly?
So like kind of like marginalizing.
Kind of. Is it like marginalizing it with some information? Kind of, but remember I've done it all just using this equation. So and we will come back to how we can then understand what are our uncertainties in our model. The other nice thing we can do now is we can just split them back apart. We put in a design matrix that had 5 vectors in and we got out 5 weights. That means that I can just take the 3 that were my stellar variability, dot them with the first 3 weights, and I get the green curve. And I can take my transit design matrix, dot them with the last 2 weights, and then I get just the transits. This is nice because then I can literally split them out and start doing things. Maybe if I was doing a more complicated analysis, I might want to fit allowing for the transits, and then I might want to subtract the scalar variability for another reason. So handy, very easy to split these things apart. Somebody was asking, I think it was Sabina was asking about systematics and when should we mass things out. So 15 minutes, we're just sailing through this. My own gratification. Maybe heard of K2? Maybe used K2 data? I used to work for K2. This is some of the weirdest space data that came out of Kepler. I will show some to you. This is an exoplanet transit, or an exoplanet target called K218. You can see in this data, which is of a star and is, I think I pulled out just a 30-day duration. It's pretty weird looking, it's pretty gnarly. We have this weird sawtooth pattern in it. That's because K2 was not pointing stably. It's a very precise instrument, but it was moving like this, and it would then get to the middle of its orbit and it would start to sort of move like this. It still is a very precise instrument, but the data had this giant systematic in it where the source would be moving in and out of your aperture. And that imparted this multiplicative effect, which was this sawtooth. And we absolutely don't want a systematic. It's another example of systematic being this catch-all phrase, well, the thing I don't want. We're going to make an assumption here, and I'm going to come back to this assumption. I'm going to say that because this multiplicative systematic is a very small perturbation, I can approximate that as an additive change. Is everybody comfortable with that? I have a multiplicative systematic, but it's only changing a very small amount, so I'm going to approximate it as an additive change. This will break down if we have really significant stellar variability. We'll come back to it. What we should do, how are we going to build a model for this? This is not a simple polynomial anymore. We need to figure out a model that's going to predict this sawtooth pattern. We're going to need to choose regressors. We need these regressors, these vectors that we put in our design matrix to be predictive of this kind of noise. And we're going to find the best fitting weights for those regressors. I'm not going to ask you what might it be, but I'm going to sort of cue up how you might think about this. If you're given this K2 data and you're given maybe an image over time, you can see these sources moving around as the spacecraft rolls in and out of the aperture. You know that there is some spatial dependency. You know that it's going to be quite bright if the star lands right in the middle of the aperture. It's going to be quite faint if the star lands outside of the aperture. And so you know, because of your intuition, your physical knowledge of what is actually going on, good regressors would be, where is the star at that time? Here is a piece of data which shows over time, where is the center of the star? Which pixel is it landing in? And then I've whitened them so the mean is 0. You can see a sawtooth pattern, which is absolutely what I expect. The source is moving around. We know with our physical intuition that this is going to be something that is going to be predictive of the flux in the K2 target. Okay, we're going to build a model. We're going to build a model that is going to fit the systematics around something that might be flexible enough to build our star model. We're going to build a polynomial in time, which is something that is going to allow us to have maybe a long-term function like we had before in time, polynomial in column position, and polynomial in row position. Here we go again with my specialty stack. We've seen this one before. This is a polynomial in time, times the power of 0 times the power of 1. I've whitened it, I've removed the mean. And then I've got row position and column position, also this is now going to, in fact, probably, this is now going to be a matrix which has columns of 1s, then columns of T, R, and C to the power of 1. It's going to be 6 across, and as many times as we have now. They're always tall and narrow. I gave away the lead. You're not going to solve this. You can't solve this for partly some of the reasons that are answering your question, which I'm going to get to. You can't solve this because it's degenerate. the thing that I have made looks like this. If I look at the first three rows in this matrix, they look like this. This is time to the power of 0, time, column to or row to the power of 0, row, column to the power of 0, column. There is not a single solution to the question, what do I have to multiply this by in order to make my model? There's not a single solution because there's 3 instances of the column 1. That means that if the best fitting solution is 2 times this and 1 times this, then it's also 1 times this and 2 times this. There's no solution, it's generated, it won't fit. You will get this error, which I understand is cut off. And it's a singular matrix error, can't fit it. Okay, great. Well, we already have an instance of a column of 1s. We will just keep that one and then remove it from the other matrices. Now that we've started talking about these matrices, we're doing transposes, we're fitting best fitting weights, the column of 1s, is it intuitive what it's doing? It's okay, it's not intuitive. The thing that the column of 1s is doing is if I take this column of 1s and I dot it with some weight, it's then just adding that as a constant. If I take my y equals mx plus c, it's c. I can take the column of 1s, dot it with my weight, which is 10 minus 1,000, that becomes my constant term. So the final term, which is, oh yeah, and then I have to do my intercept. So I can't fit 3 intercepts, it's completely degenerate. So I remade the matrix, and now I have taken away the column of 1s in row, taken away the column of 1s in column, and now you can see in this first row that I don't have multiple columns. Okay, again. Now I'm going to fit that data. I think I did that in this cell here. You can see I'm fitting to find the best fitting weights, W. Design matrix, dotted with itself, dotted with the data, I get W. This is our fit. The thing that this has done is I've got this polynomial, it's maybe letting me fit a little bit in time, but also the column of yeah, I made it a much higher order polynomial. You can see I made it a 6th order polynomial. So it's fitting that motion in time. It's not a great model, we'll come back to it. And I'm fitting the systematic. And actually, if I came to you and said, this is a model for the systematics, you might kind of squint and be like, yeah, okay, you're certainly doing it. You're certainly doing something. That red line does have a sawtooth pattern in it. It's not completely good, great though. It's not completely fit. If you look at the residuals, you can see 1, didn't do a good job getting rid of the stellar variability, and 2, didn't do a good job of getting rid of the systematics. We can improve this by including cross terms. So, okay, remember I'm K2. I did the K2 dance where I'm looking at star and I'm like, oh no, I'm not doing it right. And then I'm doing it this way, and oh, I'm rolling this way. It is not the case that the systematic is correlated with column and row independently, because sometimes I'm doing this. That means that the cross terms are important. I'm telling you this because if you're going to do methods like this, it's going to be very important for you to think about what physical processes are going on and think about what you want to regress against and why it's going to be embedded in the data. So I know that I can improve this by including the cross terms because I know that at some point the telescope's going to be this. So instead of having 3 independent one-dimensional polynomials, I'm going to create a 3-dimensional polynomial. I created a spatial polynomial. This includes row and column, and I understand that it is completely broken off, and that is very upsetting. This A-spatial is our polynomial in column, and our polynomial in row, and then all of the terms are multiplied together. So if I had 4 column vectors and I had 4 row vectors, I would now have 16, so I've taken the product of them. And then I have my obscene high order polynomial in time. Then what I've done is I've taken the cross of the time with all of the spatial ones in order to create a matrix which has all of the cross terms between time, row, and column. Bigger matrix now. It still has 18,000 times, but has 28 vectors. Now when we fit, actually starting to look quite a bit better. If I look at the residuals now, okay, flatter, sweet. Less sawtooth, great, love that. Still not completely done, still not completely fit. And maybe that's something that we were expecting. Oh, okay, all right. Does anybody have any questions about this so far? I'm going to tell you in 7 minutes one piece of information, then we're going to try doing this after lunch. And we will come back to how to make these models actually fit, which means actual reasonable stellar models. What are we going to do about weights? What are we going to do about errors? We'll come back to this after lunch. Does anybody have any questions about where we're at here? Because I'm now going to challenge one of my little assumptions. Okay, we are assuming that Y, our data, like our vector of data points, can be written as something like, I have some systematic function as a function of time, and maybe some other things too, column and row. I have my astrophysics, which is a function of time, and probably not any other parameters that we have access to. And I'm saying that in all likelihood, it's these two things multiplied together. If we say that we have S is some unknown systematic function and A is some unknown astrophysics function, instead of saying, oh, I think that it's small, and so instead of being multiplicative, I can just hand wave and say it's additive, we can instead say, well, what if I just take the log of each side, and now I've created an additive model, an actually additive model. Now I can use my design matrix to build up this additive linear regression model. Sweet, that's great. If we do that, we don't know the functional form of S, we don't know the functional form of A, we were using nuisance models anyway, saying, oh, it's probably something, some sort of polynomial over time, some sort of polynomial over column and row. We can still just use these motivated but nuisance models to catch that variability. On the screen, I have done both things. I have done one fit in linear space, and then I have done a second fit in log space. You can see that these achieve extremely similar results. So that shouldn't say time, that should say residuals. These have, and that shouldn't say flux, that should say count. The residuals are very similar. This didn't make a huge amount of difference. All that is saying is that my assumption is actually pretty good. Okay, but there's a gotcha here. You cannot do this if it is more than one source. If you have one source, you're allowed to take the log of each side and break it out into two separate components, make this into an additive model. You cannot do it if you have more astrophysics in it. Fundamentally, this is one of the reasons that things like pixel level decorrelation, self-flat fielding methods, some of these residual removing tools and methods need to be wielded carefully because they can break if you have more than one source in them. It's actually not the reason why PLD breaks, but I just wanted to illustrate. Be careful about where your assumptions break. Sometimes you don't just have one source in your aperture. Okay, I'm going to come back to this after lunch. We have 4 minutes. Do we have questions before lunch?
So in practice, how much does it matter to approximate that stellar noise level? Like what that polynomial actually is?
Okay, so I think the question is, in practice, what is, I know I'm repeating, so I'm repeating it. In practice, how well do we actually have to model the star? It is going to depend on what you're trying to achieve. If I'm treating the star as a nuisance and I want to fit lots of different stars in order to maybe run a pipeline to fit planets, I might want something that is very flexible and pretty fail-safe. If I'm fitting a given x-planet target and I want to know what is the best fit transit depth, you know, how do I fit my stellar parameters alongside all the systematics, then you want something that is less flexible and more tuned. These models are parametric instead of Gaussian process, which is non-parametric. One of the things that you've noticed perhaps as I've been talking about this is, you've made decisions. You made decisions about what vectors you're going to regress against. You baked into your problem your understanding of the universe. And should I use column, row, time? Should I use a sinusoid? Should I use a polynomial? There's a trade here, which is that makes things fairly interpretable, but it comes at the cost of I need to be somewhat right. It's hard to then ask the question, well, what if you were wrong about the order of polynomial? What if it is a polynomial but it's 6, not 4? That's where you're going to have to bring in other statistical methods potentially to figure out, okay, is this a good fit? And we are going to talk about adding noise, figuring out how certain we are in the model, weighting things after lunch. Do you have more questions? We don't have more questions. we have more questions before we go to lunch. The thing that we're going to go through after lunch is this. So I have created just two really short notebooks that go through the things that we've covered in this first session. The first one is talking about these polynomials. This is just to give you an idea of, oh yeah, how am I fitting these waves? What are the shapes? When you go through these, you can fill them out, and I've asked you what I would like you to do. You can fill these out, and then it will, once you execute them, if you execute the assert statement, it will break if you haven't done it in a way that I think is right. So fill it out, fill out A, fill out W, run your assert statement, and then it will break if I think you've done it wrong. If it breaks and you think that you've done it right, wave at me and I will come over and eat humble pie. The second notebook is a similar concept, but now it is for Kappa 10. In this, I am covering things that are going to come up later in the day. So I'm going to ask you guys to have a crack at it, and then we make a break, and I'll stop talking about it a little bit more. So we may not do a full hour of problem set because they're short. We might do, I don't know, at Brian's discretion. They don't want us to fiddle around without actually learning. After that, we're going to talk about more of the higher level concepts like adding noise weighting. And then we're going to be doing some live coding where I will show you a much higher dimensional model where we can start to fit things like test images that look like this and have tons of noise and motion and more dimensions. As well.
Yeah, we're right on time, so we'll be back to 1 at 1:30.